Having spent the last number of days talking about acceleration, the rate of change of velocity, now I want to look at acceleration graphically by looking at velocity versus time graphs. You saw a page that looked remarkably like this here a couple of weeks ago when we looked at position time graphs. Okay, remember that when we looked at position time graphs, we said that the manipulated variable was always on the x-axis. In this case, it is as well. It always is on graphs. Okay, manipulated variable always on the x-axis. So time is the manipulated variable here. The responding variable is always on the y-axis. So velocity would be the responding variable here. The graph is always titled the responding variable versus the manipulated variable, or the y-axis versus the x-axis. Now, what I want to do here for the next minute or two is just take a look at shapes of velocity time graphs, identify what they represent, just like we did with position time graphs, and then I want to look at how to find things from velocity time graphs, like we did for position time graphs. So the first one, diagram number one here, or graph number one here. We got a straight line on a velocity time graph. If this was a position time graph, what would it mean? If this was a position time graph, a straight line sloping upwards would mean? Constant velocity. Constant positive velocity. But that's not what this is. This is not constant positive velocity. Look at it. Like, look at it. The velocity here is almost zero. The velocity here is bigger. The velocity here is bigger. That's not a constant velocity. That's an increasing velocity. What do we call an increasing velocity? Acceleration. Specifically, that's a constant acceleration because although it's speeding up, the rate at which it's speeding up isn't changing. We'll say a constant positive acceleration. Speeding up. What about the second diagram? If that was second diagram was a position time graph, that would mean what? A flat line, damn it, on a position time graph is? It's at rest, yeah. But on a velocity time graph, that doesn't mean at rest. Yeah? Yeah, it's a constant velocity. Look, the velocity here is the same as the velocity here, is the same as the velocity here. Third one, if this was a position time graph, this would be a constant negative velocity. Here, it's not a constant negative velocity, rather it's a acceleration, but it's a negative acceleration, right? A constant negative acceleration. How else could we say that? It says constant negative acceleration. Yeah, say constant deceleration, or constantly slowing down, constant deceleration. What about this fourth one? Curving upwards. Yeah, Rachel, is your hand up there? No? Yep, Ben? Yeah, this not only is the velocity increasing, but the rate, listen carefully to this, it's kind of a mouthful. The rate at which the velocity increases. Does that make sense? Like, not only are you speeding up, but you're speeding up quicker and quicker and quicker. It's like you put your, how many people have a driver's license here? Even a learner's permit. Okay, so most of you do. So if you've driven a car, you know that if you put your foot on the accelerator just a little bit, you'll speed up, right? You'll accelerate. But if you put your foot on the accelerator further down, closer to the floor, so I'm not just giving it a little bit of gas, I'm giving it a lot of gas. Now, not only am I speeding up, I'm speeding up quicker than I was before, right? So this would be like putting your foot on the accelerator, speeding up, but then gradually putting your foot further and further and further down on the accelerator. So not only are you speeding up, but now you're speeding up even quicker than you were speeding up before. So we're going to call this an increasing acceleration. It's not a constant acceleration. It's increasing acceleration. Now, what do you think the fourth one is? Yep. Good, good. This is, like, be careful with this, okay? You're absolutely correct in the way you said that. A decreasing acceleration. It's still speeding up. Look, the velocity is increasing. It's getting higher and higher and higher. But it's not getting higher as quick as it was before, right? So it's accelerating. It's not decelerating. It's accelerating. But it's not accelerating as quickly. This would be like you got your foot on the accelerator, like on the floor, like right down to the floor, and you're speeding up like crazy right from the stop sign. But then you kind of ease off the accelerator. You still speed up, but you don't speed up as quickly as you were speeding up before. So we're not going to say deceleration. We're just going to say a decreasing acceleration. All right, now how do I find things from this, like mathematically? How do I find values from velocity time graph? Well, let's just draw a generic velocity time graph. Let's make it a straight line like this. To find the instantaneous velocity on a velocity time graph, remember instantaneous means the velocity at a specific moment in time. Take a guess, an educated guess. Yeah, up and over. Position on a position time graph was up and over. Acceleration on an acceleration time graph was up and over. Momentum on a momentum time graph was up and over. Remember we said whenever you're looking for a value that's on the y-axis, just go up and over. Up and over. So you're going to do something like this. You just read the value right there. Now the change in velocity on a velocity time graph. It's like finding the change in position or the displacement on a position time graph. Up and over twice, and then subtract them, right? So we'll say up and over times 2, then subtract. So up and over like this, up and over again like this, and then subtract those two values of velocity. Change in velocity is Vf minus Vi. Up and over to find the initial velocity, up and over to find the final velocity, and then subtract the two to get the change in velocity. What about the acceleration on a velocity time graph? Anyone? Give it a little bit of thought. You know this. Well, you figure this out. Ben? The slope? Is that what you're trying to say? Yeah. All right, slope works. What I'd actually, the way that I would actually think of it is this. A is equal to delta V over delta T. Delta V is up and over, subtract the 2, and delta T is the time interval, right? But that means the same thing as the slope. Just like in the last graph, position versus time, we found the velocity by saying delta D over delta T. But that was the same thing as the slope of that position time graph. So up and over, subtract the 2, and then divide by time, or just find the slope. Basically, delta V is the same as the rise, delta T is the same as the run. And finally, displacement on a velocity time graph. This is the hard one. This is the hardest one. You probably did this in Science 10, though. You might remember. Displacement on a velocity time graph. On a position time graph, it was easy, right? Up and over, subtract the 2. What is it on a velocity time graph? Like the area. Yes, it's the area. It's the area of the graph. So we'd calculate this area here, and that would give us the displacement. Okay, we'll go through a couple examples of how you find that area right there, or one example, and then you'll work on some questions. Here's the example that's on the front page of the handout that I gave you. You've got a velocity time graph here. Looks like it's hard to tell exactly these numbers. I promise you want to test these numbers, will be more clear. This should be a 3 right here, and this number up here should be 33. Okay, I think the rest of the numbers are pretty clear. What's the velocity at 4 seconds? Up and over, looks like 15, isn't it? What's the change in velocity over the entire graph? The final velocity is 33 meters per second, up and over. The initial velocity is 3 meters per second, so the change is 30 meters per second. The acceleration, well, we could say it's a slope. Somebody told me it was a slope. Who was it that told me it was a slope? He just said it in a more detailed way. That's all. The slope, or we could say delta V over delta T. Delta V is 30 meters per second, and delta T for the entire graph. Careful here, it's not 12, it's 10. 10 seconds. So we'd say the acceleration here would be 3.0 meters per second squared. Yes, 3.0 meters per second squared. And finally, the displacement. Watch me carefully on this one, okay? I don't know an equation directly to find the area of that shape. So what I'm going to do is break that shape into two shapes, a rectangle and a triangle. The area of the rectangle, I'm going to call it A1, is base times height, or length times width. The base is 10 seconds. The height, it goes from 0 to what? 0 to what? 3, yeah, from 0 to 3. So that gives me an area of 30 meters. Now the area of the second one is 1/2 base times height. The base is still 10, because the triangle still goes from 0 to 10, but the height goes from 3 to 33, so the height of it would be 30, not 33, but 30. From 3 to 33. 1/2 of 10 is 5, times 30 is 150. We add those up, and we get a total displacement of 180 meters. Your homework for tonight is the questions on the back of that example sheet that I handed out to you. I believe there's 4 of them. Please do those for tomorrow. We'll have a little fake quiz tomorrow, a little practice quiz tomorrow on gravity, and then of course a real quiz the next day on gravity.